Okay, so quick review of what we've covered so far. I mean, 3 topics basically. Topic 1, I introduced to you the idea that we're going to do a lot more graphs this year. And so we started off with constant function graphs. That's like it's a straight line straight across, completely flat. That means you would have just a number, like y equals 7. If you like my machine analogy, or a vending machine analogy, I guess, it'd be like, let's say you put in 3, you'd get back 7. So you put in 2, you'd get back 7. So you put in 1,000,000, you'd get back 7. That's a constant function. Does that make sense? Next function up from that is linear. So that would be like x plus 3. So if you gave me 1, I'd give you 4. If you gave me 2, I'd give you 5. Make sense? Just add 3 every single time. And so just keep working your way upwards. The expectation for our course is usually that we go to about the 5th or the 6th power. But I mean, the same principles apply if you wanted to go to the 10th power.
Well, grade 6s, please proceed to the stage for your pictures. Grade 6s, please go to the stage for your pictures.
So like one of the expectations would be that you'd be able to look at some of these graphs and kind of tell me what type of graph they'd be. So this one's linear, this one's quadratic, that's probably cubic. This guy right here, I actually drew a few too many little bumps that I was expecting to, but based on that, then there'd be, let's see, 1, 2, 3, 4, 5. This is probably to the power of 6. That makes sense? So that was day 1. Day 2, we talked a bit about how to combine functions to maybe make some of these graphs. And so that's where we did things like, well, like this. Here is maybe an f of x graph, and here is a g of x graph. And so what I might ask you to do is do f plus g x. So all you got to do is just literally, if we don't actually give you a number to work with, just add the equations. So like 3x plus 2x is 5x, and 3 and minus 1 is 2. Does that work? Sometimes we don't do it with equations. Sometimes I do it with like coordinate points. And the reason why I do it with coordinate points is that I can ask you for like say f of 2.
Dwayne Petluck, please dial 103. Dwayne Petluck.
It's going to be an interruption day. If I were to ask you for f of 2, and this right here was your equation, all that means to do is we'll just input 2 for x, right? So then you'd have 3 times 2 plus 3, and then that would give you 9. So you could say that 2, 9 is a coordinate. Does that work so far? And then the third thing we talked about is like shoving functions inside of other functions. It seems odd, because it sometimes doesn't seem very purposeful. Oh my goodness.
Jordan Timmons, Mary Jane Bonnet, and Michaela Cooper, please report to the stage. You're needed. Jordan, Mary, and Michaela, please get to the stage.
Sometimes we shove a function inside another function. Okay. What was I saying? Oh, sometimes it doesn't seem purposeful, but I can find you a few examples, maybe where it is. If you guys haven't finished the last question on the first assignment, maybe grab that real quick just so I can talk about how that question kind of works. The last question on the first assignment gives a word problem about a person who they have a paycheck, and 2 things are going to deduct money from their paycheck. One of the things that deducts money is they're going to take $200 off their paycheck to put into like a savings or something like that. I think it was.
For
Retirement. Yeah, okay, so retirement savings. But then the other thing that comes off their paycheck is their income tax. Does that make sense? And so the way I was trying to illustrate how you could use this is, if you did say f of g of x, making equations, that might mean first take off the $200, then take off your tax. Or if you did g of f of x, what that means is first take off your tax, then take off your $200. And the order would matter depending on which way it was, right? Like first you're subtracting 200, then you're keeping, it was like 29% off, right? Or first you take off the 29%, and then you subtract 200. So, anyways, long story short, that's a good example of like where a function inside another function happens, where often you don't just do one step and then you add it to another step. Often you do one step, and then that step has to then go inside another step. Hopefully that makes sense. Today I want to focus very specifically on this one right here, division. Division of polynomials is probably the trickiest one we have. I've kind of a little bit so far kind of talked a bit about how dividing might look. just talk you through a couple of examples here. Let's say that it ended up being x plus 3 over x plus 1, and then on the bottom it was x plus 1. What could you do to a function like this? Yeah, you could cancel. And what ends up happening if you do this is it's going to look like a nice linear graph. But what we like to do is we like to draw an open-faced circle as a hole in the graph, because you actually can't let x be negative 1. Even though you canceled it away, in the original function, x couldn't actually be negative 1. That's a possibility for a graph that's divided. The other possibility for a graph that's divided is you have like x plus 3, x plus 1, but you divide it by x plus 2. Here, nothing will cancel. So often what you get then is like a crazy looking graph where there's like an asymptote instead. So my goal today is to help give you guys some skills, though, to be able to actually do some long division of polynomials. Okay. Let's just hop right to an example, I think. Back in grade probably 4 or 5, you guys learned to do long division. I'm sure you did. And then a teacher handed you a calculator and you never did long division again. It has been a long time. So I want to kind of, if I can, kind of refresh your memory as to how long division works for dividing numbers. Because we need that skill when it comes to, believe it or not, when we try to divide like expressions on top of each other, we need that skill again. So here's a picture I found on the internet to try to describe how you divide. Okay. First thing you want to do is you want to set it up so that your divisor, usually the smaller number, goes on the outside, and the dividend, usually the bigger number, the number on top, goes underneath like the little divide sign. Does that ring a bell? Okay. Then what you want to do is try to figure out how many times can you put a 32 into the number 4. If you had 4 cookies, could you split them up amongst 32 people? No, you could not. So above it right here, you're going to put a 0 and say 32 cannot go into 4 at all. Okay. So then what we're going to do is we're going to drop down the 8 and say, how many times can 32 go into 48? So let me give you that example again. Let's say there were 32 of you and there were 48 cookies. Could everybody get a cookie? I'd say yes, everybody could get 1 cookie. And there's a bunch of cookies left over. Yeah. If you then go 1 times 32, would put a 32 right here. And so then what you do is you subtract. And you'd go 48 minus 32. So Sean, you're actually a little off. It's actually there were 16 cookies left over. Then what you do is you drop down the next number. And then you ask yourself, can 32 go into 167? You kind of got to work backwards and say, okay, if there were 167 cookies and there were 32 of us, does that make sense again? How many cookies would we each get? And this time the answer is 5. So then working backwards, go 5 times 32. So like say 5 times 2 is a 10. And you take the 0 of the 10 and put it right here. And then you like carry the 1. And then 5 times 3 is 15. Add the 1 more. Makes it a 16 right here. And then again, we're going to subtract. It means there would have been 7 cookies left over. We call that a remainder. So long story short, if you were to try to take 487 and divide by 32, your answer would be 15 plus a remainder of 7. So if there were 32 of you and we had 487 cookies, I'd give you each 15, and then there'd be 7 left that I couldn't work with. Sometimes we like to make that into a decimal number. Right? Like if you had your calculator and just did 487 divided by 32, you'd probably get like 15.325, something like that. Does this ring a bell at all? Okay. We need this skill again. Kind of sucks because who long divides anymore? Okay. Before I move on here, here's 2 little blurbs that are worth talking about. Let's say polynomials do not divide evenly. Did this thing divide evenly right here? I would say no. And the reason I know that the answer is no is that you had a remainder. Okay? If there's a leftover, things do not divide evenly. And this means they're going to be a rational function. Okay? Rational functions have asymptotes. Okay. For example, if it was x plus 3 and x plus 2 over x plus 1, does anything actually divide evenly? And you'd say, well, no, nothing was able to cancel. That makes sense? So therefore, you'd expect this graph to have some sort of asymptote. However, occasionally, a graph will divide evenly. How will I know if a graph divides evenly if I'm doing, like, say, log division? There won't be a remainder. Like, if the remainder is 0, it means that it worked out perfectly. For example, 15 divided by 3 is 5, straight up. 16 divided by 3 is 5 with 1 extra. That make sense? So anyways, if they do divide evenly, it usually creates that point of discontinuity, which I like to just say you have a hole in the graph. Does that work so far? Okay. Probably the best way of learning how to long divide these things is I'm just going to do an example, and then I might redo the exact same example, and I might do it a third time. So how about for the very first time, just watch, and then I'm going to erase it, and then I'll do it a second time, and then ask questions. Does that work? Sometimes it's just best just to show you an example. What I'm going to try to do here is take this polynomial here, I'm going to try to divide it by x minus 2. Do you think that by the time I'm done here, this x minus 2 will have something to cancel with, is basically my question. And it's kind of hard to tell because what I'd really like to do is be able to break this top thing up into some brackets, binomials. But do you guys know how to factor anything to the power of 3 yet? Not yet, probably, right? So how will we know? Well, we'll know by trying long division. That makes sense. So here's how you set it up. The smaller number is going on the outside, and then we're doing the division sign over here, and I believe this term inside here is called the dividend. So setting up kind of like long division was in the previous slide. You've got a small number right here and a large number right here. Does that work? Okay. The first thing we have to do then is say, how many times can an x go into an x to the 3? That's a very odd question. And so I'm just going to tell you the answer. X can go into 5x to the 3, 5x squared times. If you took 5x to the 3 and you divided it by x, the answer would be 5x squared. Okay. Again, I'm going to example you to death here. If that didn't make sense, I will do more. So 5x squared then needs to go somewhere up top here. And the advice I'd give is keep all of your x to the thirds in a column, because that's kind of like the tens column and the ones column and stuff like that when you're doing. So I should put a 5x squared up here. Okay. Then like in long division, what I want to do then is take this thing right here and multiply it over here to put a number down below. So I'm going to go 5x squared times x to give me 5x to the third, which it should. I just picked this number right here so that these two things would be the same. But I also have to times the 5x squared by the other half of the binomial, so that'll give me minus 10x squared. So take this guy times by that number, but also this one and times by this number. The next thing we do in long division then is we subtract. Now you got to be super careful with double negatives. 5x to the third, subtract 5x to the third, on purpose, we designed it this way, it should be 0. Like that's the whole point behind why we're doing this. Negative 13x squared minus negative 10 really means to add 10. So you have negative 3x squared. Okay, next step then. Just like with long division, the next thing you do is you pull down the next term. So I'm going to pull down a 10x. So now you ask yourself the same question again. How many times can an x go into a negative 3x squared? And so if you need to even write it out at first, you might say, well, negative 3x squared, if you tried dividing it by x, the answer would be negative 3x. So then that will go in this column right here, negative 3x. The idea then being that you should be taking this number right here and multiplying it by both of these ones. So negative 3x times by x will give you negative 3x squared. Again, we're doing this on purpose so that these numbers are the same. Then take your negative 3x and times by negative 2, make it plus 6. And we subtract. Oh, thank you. Good catch, Deb. So take these two numbers and subtract them. They should subtract to give you 0. That's the whole point behind it. If they're not subtracting to give you 0, you've not done this right. What should then happen is 10x minus 6x should give you 4x. Okay. Almost done. Pull down the negative 9. Again, ask yourself, how many times can an x go into 4x? The answer is 4. So put a 4 up here. 4 times x will give you that 4x we were just talking about. And 4 times minus 2 will give you minus 8. I'm going to subtract these things now. So 4x minus 4x should give you 0. Minus 8 minus minus 7, or sorry, minus 9 minus minus 8 is negative 1. I'm out of numbers to pull down. Okay. Unlike in long division where you can like put a decimal place and then kind of make a 0 there, we're kind of stuck now. Did this divide evenly? No, it did not. We might say there's a remainder on this. So if I were to graph this now and kind of prove my point, go to y equals. I'm going to put a bracket around the whole first part. So I'll go 5x to the power of 3 minus 13x squared plus 10x minus 9. And then I'm going to try to divide that by x minus 2. This thing should have an asymptote, hopefully. Or I screwed up. Uh-oh. Did I screw up here? 5x to the 3 minus 13x squared plus 10x minus 9 over x minus 2. Did I make a mistake? Okay, let me check my math one more time here. You know what? I wanted to do it again anyways. Did that make sense for a first run through? Ignore the fact that I'm kind of stumbling around looking at graphs here. Let me take it one more time from the top then. And then pause me if you have questions as to where I lost you. I think there should be a remainder on this one. And if there is a remainder, you should have an asymptote. But my graph is not showing an asymptote, so I'm wondering whether I screwed up. Okay. So let me take it one more time. Please stop me if I lose you. Oh, okay. Why did mine not do that? You got an asymptote when you typed it in?
There's a big long line in the middle.
Yeah.
And I went into the math and into the PowerPoint, into the math, and I did the 3 in there.
Yeah.
That's the only thing I did differently.
Maybe I screwed up typing it in then. Okay. Ignore that for now. I'll come back to that. Let me try long dividing it one more time. Just make sure everybody catches the idea here. So take your x minus 2, put it into your 5x to the third minus 13x squared plus 10x minus 9. So pause me if I lose you. First step, how many times can x go into a 5x to the third?
5x squared.
Yes, 5x squared.
So just when you divide by x, you just like say if you like x to like 4, it would just go down 1
X to
power.
the 3. Exactly, yeah. Yeah, you're basically just dropping it down a power. So that means that rather than putting something in this first column here, it's going to start in this column here. So then 5x squared multiplied by x gives you that 5x to the third again. And 5x squared times by minus 2 should give you minus 10x squared. Subtract. The first thing should always be a 0, because otherwise you didn't choose the right number to put up top here. Biggest advice I might give, I like to sometimes put this in a bracket right here, just to remind myself that the minus sign doesn't apply just to the 5, but it applies also to the minus 10x as well. So minus 13 double negative the 10 means add 10, so you have minus 3x squared here.
Would all grade 10s please proceed to the stage for your pictures? All grade 10s, please proceed to the stage for your pictures.
Okay. Then pull down the next term, so that's the 10x. Okay. So then ask this question again, how many times can x go into minus 3x squared? And like Jenna, you just kind of pointed out, really you're just dropping the power, the exponent by 1, right? So now it's negative 3x to the 1, or negative 3x then.
What are you trying to put into it?
We're trying to take this x and see how many times it could be divided by minus 3x squared. So like it would be like minus 3x squared over x is what I'm basically asking you to do. So really just drop the power by 1.
How come you don't divide by the negative?
Probably the best reason I could give is that we want to take our largest degree number. So here was our largest degree number, and here is our largest degree numbers. And so we're going to start with those ones to begin with. Yeah, like, I mean, if you put the 2 into the 5x to the third, would that really help even all that much, I would say? Because like 5 and 2 probably won't really divide all that well, necessarily. And it wouldn't even drop your exponent down from an x to the 3 down to an x to the 2. That makes sense. Okay, take my minus 3 times by x. It should be minus 3x squared. Take your minus 3 and your minus 2 and times them. It should be plus 6. And subtract. Could you grab the door, somebody? Thank you. I did that again. I did that wrong last time, didn't I? Alright, so the first two terms should subtract. 10 minus 6 should give you 4x. And then drop down the 9. I just realized why my graph wasn't looking the way it was supposed to. Just had a light bulb moment. Okay, last step. X goes into 4x 4 times. 4 times x will give you that 4x. 4 times minus 2 will give you minus 8. And when you subtract these, our remainder was minus 1. So I didn't do it right the first time. I just realized why my graph wasn't working out properly. When you're done dividing, here's a way of considering this then. 5x to the 3 minus 13x squared plus 10x minus 9 is really equal to x minus 2, that would be this little bit right here, times by the thing that we end up getting up top here is called the quotient. And it's equal to that. But since it didn't divide evenly, there is a remainder left over of plus 1. If you were to FOIL this stuff here out and then add 1, it should hopefully equal all of this stuff over here. That makes sense? Actually, it should be subtract 1, shouldn't it? Because the remainder was minus 1. Not add 1, subtract 1. I'm having a bad day so far. I'm making mistakes everywhere. I don't actually want to go about foiling all of this, but I could show you maybe a couple of key things here. Like if you did this x times that 5x squared, it would give you that 5x to the third, right? Or if you times this minus 2 by that plus 4, it would give you minus 8. Hence, an extra minus 1 to make it minus 9. I just realized why the graph wasn't working the way it was. This thing right here can still be factored. And that's why, so sometimes we're going to stop factoring, but this thing right here actually probably can still be factored. So that's why the graph is not looking the way I thought it should. So ignore that section there where I was trying to graph things. We'll get to that later. Did this make sense then for long division? Okay. Okay. I found a diagram online with cookies again. Hopefully this can help make sense of the ideas of remainders. There are 7 cookies here. I want to divide them into 2 groups. So if I want to divide them into 2 groups, each group is a group of 3 with a remainder of 1. Here's a way that you could write that then. 7 is the same thing as 3 times 2 if you add 1 more. Does that make sense at all? Well, that's what I just did on the previous slide. On the previous slide, I wrote way down here that the big mess of a number is equal to the 2 answers that we get by dividing by each other, but then we had to subtract our remainder to make it work. So here's another way you might see this written then. If you take a polynomial and divide by some sort of binomial, you're going to get a quotient, and then you're going to get a remainder. And sometimes what we like to do is take that remainder and also divide it by the binomial. Why don't you guys try one now? So I've done one example twice. Why don't you guys see whether you can try dividing this? We're going to see whether or not this thing can actually long divide evenly. I think this one probably should, but you guys are going to check. So in case you're absolutely stuck on where to start, take the small binomial and divide it into the big polynomial. That's what your first step should look like.
I don't know how to divide that into the first one.
Okay, so how many times can an x, which is this guy right here, how many times can an x go into an x to the 4? So like if you had to write it out, it would be like, well, if you had to take x to the 4 and divide by x, how many x's would you have left?
3.
Yeah. So then your first step is to put an x to the 3 up here then. Does that make sense? Okay.
And then how do you get the number that's on the bottom of it, like below it?
Okay. So then take this x to the 3rd, times it by x, you'll get x to the 4. You should. Like if you're not getting the same thing that you just had right above it, then you haven't put the right number up here in the corner. But then you have to also times the x to the 3rd by the other half of the binomial, which is a minus x to the 3rd. And then what we do is we subtract. I like to throw it in a bracket just to help keep it straight. Anybody get to this point here where when you did the subtraction of the second term, both terms canceled?
Yes.
You guys ever come across this before? Okay, you know how you're supposed to drop down the next term then? You need to drop down the next 2 terms. Does that make sense? That's how you solve that problem. Since both of these things canceled, and normally you drop down the next term, but that's not enough, drop down the next 2 terms. And then say how many times does x go into minus 3x? Minus 3 times. When you put that minus 3 up top here, don't put it in this column right here, because this is the x's column. Put the minus 3 in this column right here. So then go like minus 3 times x is minus 3x. Minus 3 times minus 1 is plus 3. And this is actually really good. When you cancel everything, you get 0. What does that mean then? Yeah, no remainder. It means that these things do divide evenly, which is good. This one we're going to graph. This one should work, unlike the last one that I tried to point out. So let's try this again here. Try to take bracket x to the 4 minus 2x to the 3 plus x squared minus 3x plus 3. I'm going to divide this all by x minus 1. What does the graph look like? What degree of graph would you call that? Yeah. This right here is the cubic graph we just created. I just prove it to you here. If I were to then put the other graph right on top of it, so an x to the 3 minus an x squared minus 3, and I'm just going to make it bold so you can see that it's... I've shown you guys how to do this before, right? How to make one graph like this thick graph. Hopefully, it should go right over top of it. Down here? Yeah. Okay, so you know how when you did this little section right here, both of them became zeros? Yeah. So when you pull down the next term, you really only have just a single minus 3x right here. So then I pulled down the plus 3 as well. I pulled down both of the next two terms. Does that make sense? And so then the question was, well, here's a minus 3x. How many times does x go into minus 3x? Minus 3 times. But rather than putting that minus 3 in like this column right here, it's kind of like you have no x's. So then minus 3 times x is minus 3x, and minus 3 times minus 1 is plus 3. And then everything cancels out perfectly. Oh, it's just because I pulled it down from the next bucket. Okay, does this graph look like a cubic? I'd say yes. However, if I look really carefully in my table of values, there is a hole in the graph on one of the graphs. So if I were to be sketching this graph on my, like on paper, although you can't see it, at 1, there's actually a hole sitting in the graph there. Because for this original graph right here, you can't actually use the number 1. Does that make sense? In terms of terminology, way back here I highlighted a slide. If polynomials do not divide evenly, they become rational functions. But this is what we just had here. If they do divide evenly, it'll remain a polynomial function, but it'll have a hole in the graph. So those two things there, they did divide evenly, that's good news, but we'd have to draw it with a hole in the graph then. Okay. So far so good? Okay. Now that I've made you learn long division, you're probably never going to do it again. This is one of those times where I'm going to show you the hard way to do something first, and then after that I'll point out that mathematicians have discovered there's a shortcut, and a faster way of doing long division. Yeah. So you can still do long division if you like, but there's a faster way called synthetic division that if you're going to do this on a test, you're probably going to do this, because most people like it better. So here's how synthetic division looks. Rather than writing it like this, x plus 3 goes into 2x to the 3 plus 3x squared minus 4x plus 15. Here's maybe a different way of doing it. Okay. Draw just a little bit of like a grid like this. And in your grid, I gotta remember how to do this properly. You're gonna put the numbers 2, 3, -4, and 15. Where are those numbers coming from? I'm not just making them up. Those are the coefficients that I had right here. Does that make sense? Okay. And then the other thing you put in your grid is this is x plus 3. I'm going to ignore the x and I'm just going to put a 3 right here. By the way, I think this is a question we did earlier. No, it's not. Never mind. Okay. Here's how synthetic division works. Take the first number and pull it down to right here. Then what you're going to do is you're going to go 3 times 2. 3 times 2 would give you 6. you're going to write that 6 right here. Then what you want to do is go 3, subtract 6. That would give you -3. I'll do this a couple times. Then, you know how you did 3 times 2 right here to give that 6 right here? There's like a shape like that. We're going to do the exact same thing, only it's going to be 3 times -3, which is -9. And we're going to put that number right here. Then you're going to take this -4, and you're going to subtract -9, which is like adding, so that makes it 5. And then one more time, you're going to do the little bounce trick we were just doing before. So now we're going to take this 3, times it by that 5 right there, which is 15. And it bounces back up here for a 15. Last step, 15 subtract 15 is 0. Here's what this means then. The last number is your remainder. So you actually have no remainder that's divided perfectly. The number beforehand is your constant term. The number before that is how many x's you have. And the number before that is how many x squareds you have. So if you wanted to divide, what was it? It was 2x to the third plus 3x squared minus 4x plus 15. If you wanted to divide it by x plus 3, it should equal 2x squared minus 3x plus 5. Let me prove it to you using your calculator then. So first I'll write out the whole big polynomial being divided. So I'll go 2x to the third. I'll add 3x squared. I'll minus 4x. I'll add 15. And I'll divide it. Shoot, did that again. And I'll divide it all by bracket x plus 3. And then right afterwards, it should be the exact same as, rather than being a fraction, it should actually have divided evenly. And the thing it should have divided to should be my 2x squared minus 3x plus 5. And I'll just make this one become bolded. So here's the first graph. And then there's the second graph right on top of it. That makes sense at all? So synthetic division is a lot faster way sometimes of doing long division, because you don't have to write everything out. You're only writing out certain numbers. So if the idea of a bounce makes sense, the first thing you do is you drop down the 2. 3 times 2 is 6. Bounce that 6 up here. Subtract to get minus 3. Then bounce again. 3 bounces down on -3 to give -9 back up here. Subtract those numbers, gives you 5. 3 bounces on 5, back up to 15. 15 minus 15 gives you 0. Then work backwards. This is the remainder. That's the no x term, constant term. This is the x term, and that's the x squared term. Does that make sense? Okay, go take a break. We'll do some more when you come back. Been sitting for a while. Work. One more thing I want to show you. Do you guys remember what f bracket -3 means? We kind of did this a couple days ago. Okay, plug -3 in for all your x's. This is going to seem very tangential. We just did a whole bunch of long division, and I'm asking you to do something very different. I promise you I have a point. Okay. So take -3 and plug it in. -3 gets plugged in. -3 gets plugged in. -3 gets plugged in. When I'm done, we should have like a number answer. I got 0. Okay, I have a point. Again, some really smart mathematician discovered something. We actually were just working with this polynomial right here on this slide right here. It's the exact same one as we did in synthetic division. Okay. This thing right here is considered to be a factor. Does that make sense? What would the root of x plus 3 be? Minus 3. Not x minus 3, but like the root of it would be minus 3. Some really smart person figured out that if you want to figure out a remainder, if you say you were wanting to divide this by x plus 3, if this is the factor you're trying to divide by, they figured out if you want to figure out the remainder, take the root of that factor and actually plug it into the equation, and it will tell you what the remainder is. I'm going to go back to a previous example and show you how I can solve for the remainder very quickly without doing any long division. Hop back to where's the one where there actually was a remainder? This guy right here. I'm just going to erase most of it. This first example, we had a remainder of minus 1, it looks like. Someone figured this out. That's why our notes today are called the remainder theorem. The theorem is, if you want to figure out a remainder, here is a factor. The factor is x minus 2. What would the root of that factor be then? Good. The root would be 2. So the factor theorem, or sorry, the remainder theorem basically says, take 2 and plug 2 in for every x.
How do you know that 2 is the root? Is it just the opposite of?
Yes. Yeah, so if it's an x minus 2, then it's plus. If it was x plus 2, it would be minus 2. If you guys plug that into your calculator, or do it in your head, I guess. Probably plug it in your calculator. Uh-oh. Oh, I forgot to square that number. I was worried I screwed it up there. Did you guys get minus 1 when you did this? This question here, the remainder was minus 1. I've just wasted the last hour of your life. I showed you how to do long division to find a remainder. I then showed you how to do synthetic division to find a remainder. And now I've shown you the whole point of today's topic, the remainder theorem. If you want to find a remainder, all you have to do is take the factor that you're given that you're dividing by, figure out its root. So if it was x minus 2, we're actually talking about plus 2. Literally plug that number into the equation, that will find you the remainder. Yes?
Would there ever be a situation where we had to find something else given the equation divided by the factor with
I would say this. I didn't show you long division and synthetic division because they're useless. They are skills that could come up. I don't know if that answers your question, but like we still can use those skills in various problem-solving scenarios. That being said, if all you care about is finding a remainder, the remainder theorem is probably the fastest way of doing it. But synthetic and long division are things that can help solve problems too. Like let's say the goal was not to find the remainder, but to try to find something else. Right? Like say your goal is to find the quotient. You know how like the quotient is this little bit up here? The remainder theorem does not do that. Is that your question? Yeah. If the question asks you, what is this going to be equal to when you're done, the remainder theorem won't help you with that. No. You would actually have to do either long or synthetic.
What's the remainder, like what is the remainder? So is that the asymptote? Or
Say that one more time?
for the remainder, like what does that show?
Oh, okay, so if the remainder is 0, it just means that these two things here do divide by each other nicely, and it probably means you should have a hole in the graph.
So that's like, no, is that the asymptote or no?
No, so then the one where they don't divide evenly probably has an asymptote. Although I just realized when I tried to do the very first graph with you guys, actually it didn't have one. So yeah, we're actually going to spend a lesson just focused on that though. So
So it just shows the hole.
yes.
The
Yeah, like basically, if it does divide evenly, then I can tell you that there will be a hole in the graph. Okay. Here's basically the terminology behind the remainder theorem. If you want to find a remainder, the remainder theorem states that if you take a polynomial and you divide by a binomial, all you have to do to find the remainder is take this part of the binomial and plug it into the equation, and that will be your remainder. It's very wordy. So like, let's say it was x minus 2. What you have to do then is go like f of 2. That'll give you your remainder. Like plug the 2 in for x. So like I said, I kind of just wasted an hour. I didn't waste an hour. It was very purposeful. I showed you a lot of useful skills. But in order to really talk about the remainder theorem, first I need to remind you what a remainder is. Does that make sense? And in order to talk about what a remainder is, we should really talk about long division. So it's actually a very simple thing to work with them. So let's try one last example here. My question here is, tell me whether if you took 11x minus 4x to the 4 minus 7 and divided by x minus 3, would these divide nicely and create a polynomial function, or would they not divide and remain a rational function? Does that make sense? Basically what I'm asking you in a fancy way is, do these things divide nicely or not?
Breakfast.
Thank you.
Breakfast?
Breakfast! What's in the Kirkland box?
I didn't think it was in this one.
Yeah.
It's apples.
Oh, okay. I thought it was cheese.
More apples. There's cheese in I mean, drink. No one gets nothing. Sean, do you want anything? There was yogurt.
Okay, if you did get 0, they do divide.
I don't know.
If you don't get 0, oh, you did. That was the one I did earlier, right?
With bananas.
You're not doing this one here, you're doing another one. You're doing this one here. Was it this one? No, it wasn't that one. No, it wasn't. Which one was it? No. This one right here. Can't be this one here then. I've got 5x and 3, 13x squared minus 9.
I keep redoing it. So I'm like, no.
What did I do?
I don't know. Oh, you're doing this one right here. Okay. So you got 2, negative 3 squared. 3, negative 3 squared. Minus 4, negative 3. I know what. This is minus sign right here.
Oh, that's 11. It's not a 1.
Oh!
You have to
You
do
got
that
that there. I'm like, oh, no.
Recalculate things you're multiplying. Okay, let me finish this last slide, and then I can be done for the day. How can we tell whether or not this thing divides evenly? You could try long division. That'll take a while. You could try synthetic division. That'll take a while. Or the whole point behind my last hour was to get to this point right here. If you want to figure this out very fast, here is a factor. What is the root of this factor?
3.
Good. The factor is x minus 3. The root then is 3. So take 11, plug in 3. Minus 4, plug in 3 to the 4. And minus 7. Anybody do that? Okay. That is your remainder.
Oh, you're right.
So, therefore, does this divide evenly?
No.
No, I'll even write a sentence here. Does not divide nicely, so it is a rational function. I would say it likely has an asymptote. If you graphed it, you probably would have an asymptote. I don't want to guarantee that, but it does not have a hole in the graph because it does not divide nicely. So, quick summary. Like I said, I went through a very long lesson to kind of make a very simple point. But I hope that in doing so, you understand what a remainder is, though. Does that make sense why I wanted to do it in this order? Because remainders are not something we rarely work with anymore. It's a lot up there. So, 3 skills hopefully you have. If you needed to, you could do long division. You probably will rarely do long division. I gotta be honest. Like, it doesn't come up a lot. If you needed to, you could do synthetic division. That one's a little more important because if you have to figure out what the answer is when you divide them, like say, if you wanted to figure out what this little bit up here is, then you actually have to do like synthetic division. However, if all you care about is figuring out whether there is a remainder or not, use the remainder theorem. And it's very quick. Okay. Okay, cool. I'm done for the day. You guys can have the last half hour to finish your assignment or work on the next one. Or if you want some textbook questions, here's some places in the textbook that has stuff. So these ones right here are probably the textbook ones. So I'm just going to pause the recording and then you guys can